Hello and welcome to our video series for our circular motion problems. So this is the problems at the end of the slides under circular motion. And this first one I'd like to solve is actually the roller coaster problem. So what we have here is the case where we have a roller coaster loop and then something like this. Part C is when you're right here in the loop. You're upside down. Oh no. Your arms, you're happy, you're having a good time. This is part C, and then part D is over here. Now, even though you're not officially moving in a circle, the path that you're moving in at this exact point is curved. And we can basically still model these with centripetal force because they are moving in curved paths. Well, this one's actually moving in a circle, but you get my idea. Let's start with part 1. So if you notice, they drew the forces on there already, but in case they didn't, you would say gravity is acting downward like this. And then if you notice, the roller coaster itself is being pushed by the surface. So the surface, I'm just going to make a longer one like that. It's actually way less, but I just wanted to make you aware of this and see it over this. But the point being is both of these are pointing down like this. Which means, first of all, they'll add because they're going in the same direction, and secondly, they both point toward the center of the circle, which means that they're both contributing to the centripetal force. So what does that mean? That means I could write this expression. The force normal and gravity are both contributing to the centripetal force. Like that. That's basically what this represents. So this is our main equation that we'll work with. Now, notice that this is different from Newton's second law slightly in that instead of ma, we do mv squared over r. And this is for curved paths. So the net force for curved paths is this one, not ma. Alright, what do we need to find? Gravity, normal, acceleration, and net force. Okay, we can literally do this almost in any order. This and this we can find, but this one's a little more tricky. So actually I'm going to find this one first. And then from this, we'll be able to find everything else. So notice that we could actually rewrite this. Force normal plus gravity, which is mg, equals mv squared over r. Just like that. That's nice. Okay. With that said, we don't know what this is. We do have mass, we do have velocity, radius, and mass, so we can actually make an expression to solve for the normal force by writing this, subtracting out the gravitational. Oh, sorry. So, why don't I do that and find this value? So this is the 500. This is the velocity, which is 8 squared. And this is the 4 meters, that's the radius, minus 500 times 9.81. Like that. Now, I purposely didn't take out the mass because I actually wanted both of these values. And when you solve for this, you get 8,000 newtons minus 500 times this is 4,905 newtons. And then, when we do out that math, 3,009. Oops. 3,095, that's what it is. Okay, I was writing it right. That's that. Okay, so our first fill-in is the 3,095, like that. Perfect. Next, we have the weight of the object. This is the 4,905 newtons. Cool. And then the net force is basically this piece right here, the mv squared over r, which we calculated as 8,000 newtons directed down. The direction comes from the direction of our centripetal force in our system, which is pointing always toward the center, which it is down, so both of these point toward the center. The last part is this one. Let's figure out our acceleration. So we can do this a couple different ways. I think the easiest is just to do v squared over r. 8 meters per second squared over the radius. Why can we use this? This is the centripetal acceleration, which also represents our net force. 8 squared is 64 divided by 4. Our answer is 16. And as always, the net force is in the same direction as the acceleration, and therefore it is down as well. Okay, so that's all part C. Let's try D. So in this case, we have the gravity acting down, but now normal force is upward. Remember, the surface can only push out. In this case, it's going to push up. So we must decide then how is this, working out in terms of centripetal force. So the force that's pointing towards the centripetal force is gravity. So I'm going to call this direction the positive direction, and this one the negative direction. That just makes my setup easier. And I always make my direction positive in the direction of the centripetal force. With that said, I'm going to write my expression for this section, so you can draw it here. Oh no, actually, scratch this. This is not that, obviously. This is the case when it's at the bottom. So this is, let me draw a picture. I just noticed the curve was in, not out. So that's a horrible drawing. Let's fix that. So this is the same loop as the one above, but we're here instead, sorry. The bottom of the loop. Glad I caught that. And that's because we have this kind of curve. Okay, perfect. Alright, same idea though. So, we're going to say force gravity is going to be in the positive direction. And then we say normal. Oh, yeah. Now that we changed this, my theory is different. So this changes the problem actually. So now if you look, force normal is now pointing in the direction of the center of the circle. And this is pointing down, which means we make up positive because this is pointing to center of circle. Now we always do that, make the direction positive in the direction of the circle, so that when we set it equal to mv squared over r, this is positive. Always we include a negative sign. It's not difficult, but it makes things easier. So with that said, I now write the following. Force normal is going to be a positive value because it's pointing toward the center. This goes against my centripetal force. We said mv squared over r. There we go. Perfect. Alright, so same kind of thing I'm going to do is actually solve for normal force and then figure out the rest. Now these are different numbers, so notice besides the mass, but the radius and the speed are different. So this will look like mv squared over r plus mg. Let's add in our numbers, so 500 times 24 meters per second squared divided by 20 meters plus 500 times 9.81. Luckily, this number, the 509.81, is the same as before. As you might imagine, your weight does not change. Like that. Now let me calculate this. 500 times 24 squared divided by 20. A much larger number. 14,400. Like that. So now I'm going to add that to our weight. And we get a really interesting result from this. We get 19,000 here. That's pretty crazy, right? This is nicely depicting what's going on. If you notice, the arrow is very big. Well, if you notice, in order for you to go in the circle, not only do you have to counteract your gravity, but the surface must push you. So this is why you feel very heavy at the bottom of a track, and this is why you feel very light. Because notice that the surface is pushing you less, so you feel lighter. The surface is pushing you more, so you feel heavier. So even though your weight doesn't change, notice the weight's the same, the appearance of light and heavy come from the value of your normal force. That's pretty cool. Alright, now filling the information, my centripetal force is this value, or the net force on our system, so I can plug that in. Now, in this case, what did we say? We said the up was the positive direction, so this is up. That's the way we set it up, which makes this one up because it's going to be the same. But now we got to figure out A. So A, you can figure out, I like just doing the AC is V squared over R. So with that said, AC is going to be the 24 squared divided by 20. Gives us 28, I'm just write it here, 28.8 meters per second squared. Squish it in here. Okay, and there you have it. So this is the roller coaster at the top and the bottom, and this explains why you feel heavy and light at the top and the bottom. Alright, stay tuned for the next video.